Hi, welcome to what I think is episode 10 of the 4coder Lexer series here. Uh, Sorry if my numbers are getting off. I'm kind of, recording ahead, so I have to roughly try to recalculate or guess how far I've gotten every time. So, where we left off, I I forgot about this. What is this? I don't even remember what this is. Clearly, I thought it was a bad situation. Let me just remind myself some of these details here. I think this was all stuff I've already dealt with, right? This is just distracting me, though. We built the condition set stuff. Right? Right, so I build one out of a set of inputs and a set of fields, and that gives me a condition set constructor that can't construct any condition set, but it constructs the condition sets I actually need to start with. And then the ones that I need that are more complicated I get from unions, intersections, subtractions. And so yeah, that's all implemented. Cool. So that means that the next thing to do, where was that? Sorry, I'm bouncing around here. There it is. So this needs to get redone. So simplify transitions. The way this works is we're trying to, in simplify transitions, the goal is to reduce the number of transitions in the system by finding ones that cover cases that are already completely covered, or in other words, to find transitions that can never actually execute, right? By identifying those, we can remove them, and therefore not spend any computation or optimization work on those transitions, which will make, will improve how everything else works. It will let us eliminate more states because we'll be able to easily say, like, here's the set of transitions that can actually possibly potentially occur, and then when we look at everything in those transitions, we can say, like, here are all the states you can actually possibly reach, and then you can remove more states, and then so on, right? So we get the ability to simplify down the set of things we have to work on in a lot of ways by starting here, I think, which is why it works this way, why it's set up to work this way at least. So the problem is, when I first wrote it, it was written on this old idea of a transition case that was simplified, and now we have a full condition set as the thing. So what I want to do is remember how this structure works here. I'm visiting each state. For each state, I am visiting each transition. For each transition, I am visiting all of the previously saved transitions for that state, and I'm doing this opt eclipse thing. Now, I don't think we need case eclipse anymore. I think what we need is, if I'm looking at these, we're basically, before any of this optimization happens, we're going to have to add a type checking stage, which I put it in the wrong spot. It really should go here. There will be a type checking phase that'll make sure we're not, I want to show you what I'm talking about. So in this transition case, there are two different kinds of transition cases, condition set and delimiter matcher, and we want to make sure that we're not finding any of those. So if we're going along and we find the delim match, then we shouldn't process it at all. In other words, it should always get kept, and we shouldn't keep looking at anything else in the state, because the type checker will have already passed and said that this thing is set up correctly, and there's nothing we can do to optimize it then. So, transitions first equals 0. First, yeah, before we do anything else, we want to look at this and say, is delim match equals false if the first transition case kind is a delimiter match, then it is that. So then finally, If it is not a delimiter match, then we go ahead and do this work. That work will not work on delimiter matches. Okay. Second, now what we have is we know that we're looking at condition sets. Everything in here should be a condition set because the type checker won't allow this to go with this. Like there to be these after these, basically. So the first one will be a condition set, therefore all of them will be condition sets. So next what we do is for each transition, look at previous transitions. I feel like I'm gonna... Apologies. For each previous transition, we want to subtract out basically everything that the previous transition gets to go first. So if it matches the condition, then it'll go. So any condition a previous transition can handle, later transitions can't handle them ever because they both are the same condition. The first one, whoever goes first, right? So what we want is essentially while we're doing here we grab that condition. What I'm going to do is say we're asserting here that the condition kind is a condition set, and then we are grabbing the condition set, right? And then what we're going to do from then on is at each stage we're going to grab one of these. So previous condition from the previous transition, and assert again. Well, we don't need to assert that. That's like a super redundant assert. But what we can do is say the condition set gets updated to the SMI condition set subtract. I pass down the let's have the primary context, so that has an arena in it. I pass down the condition set and the previous condition set, right? And that updates my condition set. Now, if the new condition set, if I remember correctly, the way these work is a condition set is made up of a chain of nodes. If that chain is basically a set of sub-sets that get union together, right? So if that is 0, we have an empty set. So once we have no nodes left, we break out. If we get to the end and the condition set count does not equal 0, then we have a set that still has something worthwhile left over in it. And we update the transitions condition by saying, okay, your condition.condition set is this new condition set, and we push that transition node onto the new list of things we're going to keep. Then finally we output that list when we're done, right there. Okay, so that I grabbed the transitions, the first transition, but I still need to look at its condition.kind. That's what I need. Whoops, I keep hitting F1. It's F6. I think I've had this problem before already. What's going on? Alright, so what's going on here? Okay, so the sub-recursive thing doesn't actually need to have a return, is the only thing happening there. Whew, okay, so simplify transitions is now implemented on a full set system. What I want to do is, I can't run this because I don't have the type checker and it's just going to hit that assert, right? If I do want to test anything, I can just run this and make sure that it is actually hitting that assert as I expect it to. Because if not, then I might be hitting something else instead. Okay, so I have a bad pin pointer. Where did that come from? This list looks somewhat uninitialized in a weird way. I forget, it's been a long time since I've played with C++ allocation, like the things the debugger poked in, but what is bad food code? I forget. I should go look it up. Condition node sub. So it's trying to simplify transitions. It's trying to do a copy on B's fields. B is this thing right here. Okay. Okay. Alright, let me quickly look up what that code means, just to get a hint about what this means. Come on, well, just tell me what it is. Visual Studio, bad food. Okay, so it's allocated but not initialized. Okay. So I have a pretty easy way of fixing it so that I can avoid at least having any uninitialization or uninitialized memory bugs. Does that catch it? Is that all there was to it? Does that give me a null pointer? Oh, that's bad behavior. What was going on here? How did you simplify transitions without crashing? Okay, well, the whole thing runs without crashing. Well, at least unless I step over CRT's closing code, I guess. Wait, no, this isn't crashing. It's just I stepped out of into that, I guess. Alright, whatever. Don't care. Probably because I'm not returning 0 down here, I'm not sure. Actually, I've never understood why that's even allowed. Anyway. I don't understand how it could possibly be not crashing. Oh wait, I put the check in right here. So I see, I'm not type checking, but I also happen to have a typed correct state machine. So at some point it is going to hit this, and then it's not going to... That's... okay. Sorry, it's not going to crash. I didn't just put in the asserts, I also put in an actual if. The only thing the type checker would do is make sure that this if actually checks the correct, like, has the correct result by ensuring that I'm not going to see a pattern where a delimiter shows up later. But I don't have a pattern like that, because then I wouldn't pass the type checker. But what I have that would pass the type checker, and therefore this part is fine. Okay. That was a little misunderstanding in my head. Okay. So now, what I kind of want to see is, after, I mean, I still don't understand why I was getting, maybe the uninitialized memory also included the count, so a count was probably getting wrong, so I had a count that thought it was non-zero when it should have been 0, and by clearing everything to 0 I got rid of it. That seems like the most likely explanation. Or there was maybe a null pointer check that was not returning null because the pointer was filled with bad food instead of 0. Something like this. Now that it runs all the way through that without crashing, what I want to see is, can I explore this and actually see if it makes any sense? So the root has 20 transitions in it. I want to kind of look at like what they look like. So the first transition has, it has a next, a condition, an activation. I'm going to move, I'm going to grab this here and just call this transition pointer. And debugging is an unsolved problem. There we go. So my first condition set is not going to be altered at all, so it's not surprising that it only has one node. That one node says all inputs are valid, right? Well, not all inputs, sorry, all flag sets are valid. So it has a list that is empty, right? It has one empty list of pins to specify that it's a set with all possible flag combinations combined with the end of file. Right, that's the first thing I put in there. So end of file is handled right there. Okay, so there's my first condition. What happens if I go to the next transition? Probably have more luck printing this stuff out. I kind of think that's what I should probably do today before I do anything else, is let's just print out the simplified state machine to see what it looks like after after it's gone through the simplification thing, and also make sure that iterating it is still, it's not got null pointers in the middle of linked lists or something that are going to be bad or anything like that, right? But before I get straight into that, here's the next condition set. It also has one node. Fields are open to be everything again, and inputs is an array of inputs with 50 characters in it. That's probably for catching identifiers. What is the next one after that? I'm pretty curious. The next one after that is again a condition with 1. It's got an empty list, I bet. Yep. And its inputs 128. So that's for the UTF-8 characters. Alright, the next one is where it could start being maybe slightly interesting, potentially, but possibly not at all, or something. I also want to check these destination states. Alright, so here's what I propose we do. I kind of want to, before I move ahead, I feel like we're flying a little too blind. I've been feeling this way for a little while, but it takes me walking away for a day and coming back to have a fresh perspective. I just want to have like an opt debug dump. 4coder. That was weird. It's like my window lost focus or something. Okay. Okay. That's not really an opt thing. That's just gonna be, I'm just gonna call this like debug dump all by itself. It is nothing else. Maybe I want to call this like debug print transitions or something like that. Maybe I'll have more debug category things later, so I don't want to just assume that dump is descriptive enough. And the context, primary context, what do you have? You have a root. So what I want to do is I want to say, let's look at, for every okay, there's a couple of different ways I could do this. I could do an iteration over the set state, and then for every state print it out, and that's just that. Or I could do an iteration via the root and using the mark excluded thing, so anything that's not been marked will need to be printed and then marked, and then all of its neighbors that aren't marked get like recursively called to, right? Well, all of its neighbors get recursively called to, but they get ignored, like they quit out the call right away if they're marked or something like that. So that's option 1 and 2. Which one do I prefer? Well, what is the upside and downside? The upside to doing it via iteration from the root is that I'll kind of get them in a particular, like, predictable order based on their structure. The upside to doing it from the state is I'll get to see which ones are actually included in the list. So if anything got optimized out or did not get optimized out incorrectly, it'll kind of become apparent, or at least it'll be possible to notice that it will be the log or the print would contain that information, even if it took a little bit of investigating to discover that information. It would contain that information. So I'd have a chance of spotting more bugs if I did this, if I stared at it long enough. I think I'll do that way. It's also just a little bit simpler to implement that way, and simpler to implement is kind of the point with a lot of the decisions in this piece of the code. Like, I know this whole set thing was not simple to implement, but it was also the simplest thing I could think of for representing the information I needed to represent. So in that sense, it is the simplest, and thank goodness I'm not doing that at runtime, right? Okay. Because, man, would it be pretty sloppy as a performance concern, like a pretty performance, it would be pretty sloppy if I was doing that in performance relevant code, all that set stuff. Anyway, context states first, for each state, and then what we're going to do is, this is a lot like simplify transitions actually. We're going to visit each state, we're going to get your transition list, and then we're going to iterate your transitions. For each transition, we are going to print stuff out. So I kind of want to do stuff on the state as well. So let's take a look at what's in a state. So this doesn't have like a pretty name. I'm going to give it one, and we'll have to figure out how to fill that. So that kind of argues for something slightly different. Pretty name. How are we going to do that? I guess for now we'll just use a macro and keep it the way it is, and then when I want to switch to type checked, like out of order declaration of states, then the string literals will provide the pretty names. That's how we'll do that. Okay. Then everything else, I think, on entry actions. Yeah. So the rest of it's all kind of in the transitions themselves. So for each of these, what I want to see is the transitions. Again, I'm like losing, my window's losing focus or something, or I'm getting like in a weird state. My keyboard inputs are getting ignored until I click the window again. Weird. Okay, iterate the transitions. For each transition, alright, so if we have a delim match, transitions, destination state, pretty name, and then I'll probably want to include an activation list printer as well. To take the activation list, iterate that. Guess I'll just switch on the kind of action it is to completely determine how I print it. I need a 4coder command that turns a list like this into a set of cases. I don't have it. I do this kind of manual expansion all the time. And there we go. Okay. I'm going to ignore the parameters of these for now and just list what they actually are. As that's kind of going to be enough information to figure out what's going on. And, okay, so all of this actually doesn't need to be underneath the if at all. That's all sort of stuff that applies no matter what the condition of the transition is. Now if we come back over here and look at the transitions condition, what we will see is the other option is a condition set, and I want to print that as well. fprintf transition on condition set, and then I will have to iterate all the stuff in there. fprintf, hold on, before that let's look at the nodes. I said fprintf on all these, and I don't actually want to put the standard outs in them, so I'm switching them to printfs. Okay. Alright, this feels like it's been a good use of time. I'm only halfway through an episode. and I've got to the point where I'm almost going to be able to show something for all this work that we've done in the last 9 previous episodes, where I haven't done one thing to inspect how things are going yet. It's a little bit actually unusual. I usually don't go more than a couple hours without finding a way to inspect my results, but I think the format here has caused me to behave a little differently. I have to focus a little more while I'm making these videos moving forward. So, for each node, I'm going to want to look at, I want to kind of be able to see these as close as possible to the way they're actually just structured in memory, right? But it's fairly deeply nested, so I'm trying to think of the best way to print this. I definitely want for there to be a way to look at each node. On each node, there's these fields and these inputs. Now, the inputs aren't that hard to print out. I can just do that right now. So, inputs, and then I'll just say like how many of them there are, and that'll be that. So node, a condition node inputs. I don't need to see the list of inputs right now because this is just for summary purposes. So the count will give me enough information to kind of figure out what's going on. Hopefully. Maybe if that count is small enough, maybe we'll do it like this, just for the sake of slightly extra clarification. If there's less than like 10 characters in there, and they're all ASCII printable, lame. If they're not all ASCII, then if they are all ASCII, then we're going to printf like a little thing that'll like list them for me, and then I'll stick them right here. Okay, so we need to make a quick digression over here to my base types. Character is, I have all these character is functions. I just want a quick character is ASCII. So all we have to do to check if a character is ASCII is it needs to be, let me pull up an ASCII table. When I say character is ASCII, what I'm really saying is this character printable? Maybe that's what I should call it. Character is printable ASCII. Right? And so the following things are printable ASCII. If the C is a space, yeah, this is actually going to be fairly specialized. I don't know, is like line printable ASCII or something like that. So if it's a space, basically it's going to be like this. If C is greater than or equal to space, or let me reorder this. If it's in the range between space, which is the lowest thing in the ASCII range before all the, except like new lines, which I can't put on a single line, and tabs, which you can't really read either, space, all the way to, I'm going to just call this character is basic ASCII. That's what I'll call it. There we go. Alright, so that's how I can print the inputs pretty cleanly. And then once that's done, we're going to printf a separator from that and the fields list. And the fields list is basically just going to be a series, like a list of those things I did over here. Let's see if I actually have them still. Do I have like the, no, I don't have them. So when I was showing like field sets, what I was doing is basically saying like a field set is like this, right? So I'm gonna just take like this, right? And say like, okay, the set is like this. Right, whatever. Right, whatever. The union of each of these things, where each of these things is essentially like, this is half the set, this is a quarter of the set, this is a quarter of the set, and I'll be able to just piece together from that what's going on. So, I'm going to go, there's my input portion, and then here's my fields portion. And then when that's all done, finally a new line at the end. And so inside the fields portion, what we're going to do, first let me go back to condition node, fields. So a field set has a count in it right away, that's good. So I'm just going to iterate these, I guess. And what we want to do is say output a comma unless this is the last one, or I guess unless this is the, we'll do it that way. So if node next does not equal 0, then we need to print out a comma space. And then what else do we print out? Well, first let's figure out what the node is. The node is a field pin list. I'll call this pins, which we get from the nodes fields first, right? And we'll call these all pins, and then what we have to do is we need to know how wide this thing is. So what is the width and we can answer that question way up here. Field bit width equals context flags flag set. Yes, this is where I need the count. Okay, so that gives me the number of bits I need. I'm going to turn this into like a capital X, and then well, actually lowercase x will work, but I'll use stars. Okay, field bit width, and then yeah, I'll do it this way. Push an array onto the context arena. It looks like this. For each step, we're going to block fill with a U8 the field memory. Let me look at the parameters here. The size of that is field bit width, and the thing I want you to fill it with is stars. And then we're going to iterate this list here. Field pin equals pins first. Look at each pin. Right. So I need to have numbers on the flags, but we'll be able to do that. Flag number equals, we look at the pin, we look at its flag, we look at its number, and then we set field memory flag number equal to. Then the question is, what is the value of this, right? So it's going to go look at the pin value. If that is a affirmative, then that, and if it's negative, that, right? And then we need to make sure our flags have numbers. They do. Do we actually set the flag number when we simplify flags? We don't simplify flags anywhere. Do we ever set the flag number at all? Add flag. Add flag. Push rate 0. Yeah, I think these are all just going to have their numbers set like that. So let's just add in a quick thing right here that, like, before we do all this, discard all excluded states. Opt simplify flags. So for now, opt simplify flags is going to be just a thing that numbers these things. So I don't even number the states yet. Okay, actually what I'm going to do is flags number. Set numbers or something like that. That's going to do a loop. I'm going to do this down here. Alright, a loop over primary context. Flag. For each flag, set the number equal to the number we have here, increment our number, and our first number will be 0. Okay. So flag number is now trustworthy by the time we get to debug print transitions. So just make sure we're actually calling this properly. Flags set numbers. Okay. So now when it goes to do this work, it does that field memory stuff, and then finally we're going to printf field bit width, field memory. Okay, so now the only remaining problem is that we don't have pretty names. So when we add a state, we want to make sure that in addition to everything else it does, add state expects a pretty name. And so then when we get one of these states, where do we actually call this? My add state, yeah. When we get one of these states, what we're going to do is, in addition to pushing that there, we're going to set this pretty name to push string copy using the primary context arena of that pretty name, and then this is going to expect a pretty name, which we can put there. And when we build now, we should get all the errors for where we can't actually do that. Begin state machine, so this will have a pretty name that's built in of root or something like that, right? Good point. All right. Now we don't need all that extra noise. Here we go. Okay, so now what we need to do is wrap these in a macro for at least the time being. It's going to look like this. Now kind of what I actually want to do is not actually have to call add state explicitly if I don't want to, and just pass names into these other SM things. So like down here, for instance, I'm passing identifier to SM case. I kind of want to redo the typing on this a little bit so that this takes just a string literal that says identifier, and then that way I don't have to declare all of my states here. I can just do them down here, but maybe that's not really worth it. I'm not sure. I'm like torn on it. But not having to maintain this list of states that could actually be derived from the state machine would kind of be nice in my opinion. It's just I'm not convinced that the implementation effort will be worth it. So it's like a frustrating situation where it's about not being giving up on an ideal because of, you know, maintenance constraints. So now what we need to do is just anywhere where we see space equals space sm add state parentheses parentheses semicolon, we want to replace that with parentheses semicolon. And then anywhere where we see state pointer, we want to replace that with add state open parenthesis. Okay. Is anyone else nervous, or is it all me feeling that? Hey, that's pretty cool. I want to look through all this real quick. So what we're going to do is see if we can get this to run over here in 4coder. First of all, does my project have a way to run this? Run generators on F5. Let's try that. Hey, I wouldn't want that. Okay, run generator. No, please do not use the footer panel. Reload the project, run generator. There we go. Ooh, that's a problem. Please use the run buffer though. Load project. Boop, boop. There we go. So, we have, okay, it's not quite right. Inputs, main.cbp, inputs, yeah, so you need to be tabbed over actually twice to really be readable. Okay. Cool. So now we can see, like, okay, it's saying like the inputs 0, 1, 2, 3, 4, 5, 6, 7, and 9 operator or f number dot? Why not 8? Also, where are the rest of the transitions? So I feel like I'm not iterating the transitions correctly or something. Ah, that's why. Alright, to really be able to read these transitions, what I probably need to do is have the things that come underneath the transition rule be tabbed twice. So anything that says tab here is going to become double tab. So, on this input, consume emit go to root. On this input, consume go to identifier. On this input, consume go to identifier. So this and this are actually both doing the same thing. So why aren't they in one state? Because this 128 is just a convenient way to write the thing. This is a range of 128 characters, whereas this is scattered 50 characters that just happen to also do the same thing, and so they get expressed as, like, these always go together, but these 50 are specific in this situation, and so it just happens to work out that way. So, for instance, if we were trying to emit this as a lookup table, then the fact that these look as separate cases was irrelevant. But if we were trying to emit it as, like, handwritten control flow logic, if we were trying to emit, like, all of this as like go-tos and checks, we would want some logic on here that, like, turns this into as few conditions as possible, right? So, like, one would be check and see if the high bit is set, then this works. For this one, we would need to find a way to break it down into the fewest number of possible fit checks to determine you're in this case, right? And that would basically be like a couple of ranges with a couple of exclusion rules, or maybe a few more extra ranges to pop out those exclusion rules or something like that. That's kind of that's a level of optimization problem that we don't necessarily have that much of an interest of getting into, like, the weeds with. Hopefully we can just drive it from an acceleration table, in which case it won't matter. Here we can see capital L, little u, capital R all have special rules. This can go to pre-R, which does can transition to either identifier or to a string literal. These can also transition into string literals, potentially. Not sure what these 5 inputs. So these are the 5 whitespace inputs. So here, this is kind of neat. So here, this is a transition to whitespace end PP. Now, what is whitespace end PP? Whitespace end PP is this thing here that transitions to whitespace. You can see that this has no consume in its action list. So it basically says on all inputs, transition to whitespace without reading whatever you saw. So this is a perfect example of being able to peek ahead will allow us to do better. So up here, whitespace end PP, we consume that character and then we go here. But then what we're going to want to do is have a thing that says, hey, whenever you go to a state, make sure that that state isn't actually just a thunk to another state, because this one is, and so what this could actually do is just go straight to whitespace. Why does this exist if it's just a thunk to whitespace? Well, in the code that's right now in the model, this transition into whitespace has 2 set flags, and you'll see that anytime anyone ever goes to whitespace NPP, they also have a set flag in front of them. Why do they have that? If the set flag and set flag I set are on the state, why are they showing up here? Well, remember, at one point, one of the optimizations we've already done is to do these 2 stages here that take all the actions off of the states and put them into the transitions. So these actions were actually originally grouped here, but they've been taken off of here and put into here, and also been put up into here. And so these 2 set flags are kind of bound together by the fact that they are defined in one spot, and then they're being spread out in a way that is sort of predictable algorithmically as an optimization that we're you know, taking advantage of the fact that we don't actually need on entry actions. We always need transition actions. So we don't want to have to specify that those two set flag things happen in several locations, so we're putting it on the state, knowing that the optimizer will blast those out to where they actually belong. But we also kind of want the optimizer to now finish cleaning up after us and take whitespace NPP completely out of the equation and link us straight to whitespace. So how would we ever make it do that? Well, we would need it to recognize that if it sees something like this, where it's never consuming its input, then this is actually a thunk state. So we want a special rule that's like, look, someone who never consumes their input is unhelpful. Now there are two ways we could achieve that. We could have a special case rule that's just like check for through all states and see if any of their transitions ever do a consume action. If none of them do, it's a thunker state and we can just rewire it. The other thing we could do is just do the thing that pulls forward. So this here is saying always go to whitespace. Well, it says on all cases go to whitespace. So here are all cases that whitespace can handle, and these, with the exception of this one, all consume. So it would pull that forward, and then this would actually have to pull forward again. So what happens is this would say go to root. Well, root is hanging out up here. State root is hanging out up here at the top, and you can see it's going to end up pulling forward all of these things that happen that it didn't already know how to handle from the root handler. So the root handler says, here's all these different things that I know how to consume. So if you ever don't know how to consume something and you say don't consume this but transition to root, it's going to end up, when we do this optimization, pulling in all of these into those other places, thereby getting rid of that extra move to the root and just doing the consume, emit, go to that these do. So like you're consuming whitespace, and then you see a character that would begin an identifier. Well, the way the model is set up, you say, well, I don't really want to have to handle all, like, I don't want to write the input handler for this, and the input handler for this, and the input. That's all already contained in root. Why don't I just say, I'm not consuming this, and let root handle it? But really what we want is we want it to say, okay, I understand that that's, like, the way you want to specify this, but the way we want it to actually run is to the way we want it to actually run is to, at the first moment it consumes the character, know what it's supposed to do with it. So we need to pull these forward until every single series of these actions has a consume in it somewhere. Now the consume doesn't always need to be the first thing that happens. Let's look through here. I'm sure we'll find an example already where someone maybe emits before they consume, although maybe not. Maybe we always consume first if we can. I'm not sure if we have any pre-emits yet. Maybe that'll only be, maybe I'm wrong. I think consume actually does come first always in the current status, but there's no reason it has to. It's totally possible to, like right here, you see this does an emit of its current state and then, or like an emit of its current token, and then it goes to root, right? So one thing I haven't seen any example of yet is these flag states here, right? I guess I know why we haven't seen an example of it, which is that the flag states are just that simple so far. But sooner or later, we're going to start seeing these flag states get more complicated. Pretty much all of them right now are just saying, hey, I handle all possible flags. But what I'm expecting is that sooner or later, we'll start having situations where, yeah, we don't have a single one yet, where there are like chains of these. And I guess the thing that simplifies transitions just doesn't happen to create any of those yet. But we do have cases where we see ones and zeros showing up there. Let me see if I can find one. Like I'll go to one where I know we have one. So the string state, where is that? The string state, for instance, has a lot of rules about what it does on certain flags. So actually, those flag rules don't make any sense. This is essentially saying that it only has transitions that apply when it's got a 0 there, but that's not correct. So this looks wrong to me, and I want to find out why it looks like that. Let me make sure I'm printing it right first. So when we go to print we are getting different inputs every time, so it'd be surprising if we were not getting the fields from the right place, and I think we are. So the fields must be wrong on that node. So let's go and look at what this model I've written out actually says its fields are supposed to look like the field specifiers on its conditions are supposed to look like. Because I have a feeling that this is getting spammed out to these in a wrong way when we do subtractions or something. I'm not sure yet. But it's like, it definitely looks like here, this and this should be redundant state, or transition rules, and they haven't subtracted each other out. Like, this did not subtract this out correctly or something. Or when it, yeah, somehow it didn't do the right thing. And furthermore, there's like no fallback handler or anything here, which is really weird. Like, this only has 1, 2, 3, 4, 5 characters it can handle. That's just wrong, you know? Here's another example of a thunker state, by the way. This literally does nothing except go to string. So anyone who says they go to character should just go straight to string. Anyway, let's take a look. By the way, what I was going to say is once we pull forward those actions, right, we've done the thing that pulls forward all of these so that we always do a consume and always go to a particular state, we might be able to then simplify states again, right? Essentially, when we look at, like, okay, character, for instance, we're going to end up being able to say character is identical to string because it always does nothing in transitions to string. So anytime you go to character, it's the same thing as going to string. So once we pull all these things forward, we'll still have people who say they go to character, but character will be identical to string. At that point, we might want to run a state machine optimizer that looks for identical states and collapses them into a single state. And that way we would reduce the number of redundant pieces of code, even though we wouldn't necessarily be speeding up what a control flow version of the code would look like. It would be important to reduce redundant states for a lookup table accelerator, since lookup tables grow with the size of the states when you're doing them, right? Okay, so for now what I want to do is I want to look at cpp.cpp. Why does my string state look weird? So I have quote with is chars false, a separate one which is quote with or single quote with is chars true, but that didn't show up. Then a backslash with no flag rules on it at all, which didn't show up correctly. And then a peak case, which does show up as a peak. But that should not have any flags on it. And then finally, down here we have several more transitions that got lost completely. So I want to look specifically at, I'm going to walk through the code that is trying to simplify the states for the string state, because that looks like it went wrong. So simplify transitions. All right. Right here. And that's what we'll do in the next episode, is we'll figure out why my simplified transitions is messing up the string state. All right, see you then.